Thunderbird Robotics is a Canadian-based team that's an amalgamation of 3 teams that entered the 2005 DARPA Grand Challenge: Team Thunderbird, West Coast Robotics, and Team Schleppner. Our vehicle is a stock 1991 Jeep Cherokee that we call Snowstorm. Its primary sensor is an IBEO scanner, a high-end automotive device that comes with its own computer and software. Note the stereo camera mounted above the IBEO. Here's actual output from our IBEO as Snowstorm navigates past a parked vehicle. These 2 devices are able to recognize, track, and classify vehicles, bicycles, pedestrians, and obstacles, giving position and velocity of each. This covers the front 200 degrees of Snowstorm, while aft we've mounted a SICK laser scanner to cover the rear 180 degrees. Other sensors include GPS, odometry, and IMU, which are integrated into the vehicle. All our actuators, throttle, brake, steering, and gear shift, are mounted in a single box located in the driver's seat, together with laptops that perform all of the computer processing. We currently run Windows, but are considering shifting portions of the software to QNX or Linux. We have a drive-by-wire game controller on the passenger side, so that the person in the right-hand seat can drive the car or function as a safety rider when the car is under autonomous control. Labeled manual e-stops are on all sides of the vehicle. Snowstorm is parked at position 1.2.4 on the NRC course. John Hallam will now start up the vehicle in autonomous mode. It gives a 5-second warning before starting. Note the alarm has been silenced here for this test so you can hear me. The car moves out on its own, accelerating to 16 kilometers per hour. Now John applies the wireless e-stop, and Snowstorm stops with the brake lights coming on. Now John unpauses the vehicle and it starts up again. Our e-stop system can be easily replaced by the DARPA-issued e-stop. Let's tour the full course, a parking lot behind the Fuel Cell Lab south of the UBC campus. Snowstorm starts at position 3.2.7 on a figure-8 route with a short connecting road. Each circle is 2 lanes one way, including the connecting road. Lane edges are marked by cones at the end of the parking stalls. Snowstorm avoids an obstacle vehicle as it drives to position 1.2.6. Snowstorm leaves the parking area, driving to position 1.2.12 and making a right turn onto the other circle. We drive to position 3.2.7 and a left turn puts us back at the start. The total course length is 330 meters with all waypoints painted as orange dots about 13 meters apart. Our first autonomous obstacle avoidance test was a big success. Note how the vehicle stops when the IBEO recognizes the parked vehicle. Snowstorm then turns to the left, following the cones along the left lane, and passes the other vehicle. After completing the pass, Snowstorm returns to the correct lane and completes its test. Here's another autonomous run to further test our obstacle avoidance that was done on Easter morning, April 8th, as the sun was coming up. You can hear the birds singing the arrival of the sun. Note how Snowstorm moves to the left to avoid the parked car, and then returns to the correct lane position after passing the vehicle. Tests like these are providing us with great information to fine-tune our software algorithms. We're using 2 simulation programs to perform bench-scale software testing. The first is USARSim, maintained at the NIST website and adapted by our team with sensor inputs, Snowstorm outputs, to make it capable of performing the tasks required of the Urban Challenge. Our second simulator is SciCore, a home-brewed package developed by Dejan Cesar, our team manager. We've been running our site visit course in autonomous simulation mode for about 2 months, but only achieved autonomous operation of Snowstorm this past week after many trials that showed the system to be very brittle. We've made significant progress this past month, but still face several localization problems. Our differential GPS has not been activated, and we haven't yet integrated our vision system. We are installing a front-wheel direction sensor and expect these improvements to push our autonomous control to the necessary level. We're also designing a precision 2D odometer based on the optical mouse. Overall, we expect to present a highly competitive entry when DARPA officials visit us at the Bremerton Motorsports Park this summer. We look forward to showing you our progress at that time.
And we finished, 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 and we finished.